All right, good morning, everybody. My name is Bill Lotko. I'm sorry I have not been able to come to more of the lectures, actually any of the lectures earlier this week. It's been a very busy time for me. My home is Dartmouth College. I'm at the Thayer School of Engineering. Dartmouth has kind of a split space science contingent, about the center of mass is in the physics department, and there are a number of us in the engineering school as well. Truth be told, people in the engineering school tend to do more theoretical modeling than experiments, and vice versa in the physics, which is something you might not expect. My research involves modeling of geospace, and in particular, in recent years, I've been focused more on global and system interactions between the magnetosphere, ionosphere, solar wind, and even the thermosphere to some extent. But I started my career in microphysics, and it's never quite left me. And there's a lot of fascinating things that goes on in microphysics, but for me, the interest is how that figures into the overall system, how the micro affects macro, and vice versa. And I'll give you a little bit of flavor of how those two things come together in the next couple of hours, I guess, including our break. And so I'd like to, actually, before I get started, let me just ask, I'd like to understand a little bit more about your backgrounds. So how many of you consider yourselves more, say, in solar physics or something in that ilk? Okay, good. Familiar with the MHD equations? Okay, great. I teach a course on MHD at Dartmouth. And how many interplanetary, consider yourselves more interplanetary medium? Heliospheric? Okay, more or less, yeah, it's a very interdisciplinary area. Geospace, and let's take that in two parts, magnetosphere, solar wind magnetosphere. Yeah, okay. And then ionosphere, thermosphere, atmosphere. Yeah, good. Okay, there's Jan back there. And planets. Anybody working on planets? Well, Fran, such an enthusiast. Let me say that more emphatically. Evangelist. Okay. I saw the end of her talk yesterday. So, have I missed anything that astrophysics? Anybody mainly astro? Okay, astro. Good. All right. Good. All right. Well, this lecture, or these in two parts, could be generalized to include magnetospheres of planets. I like to tell my students when I teach a class in the fall and winter, an engineering design class, that there's only one class that's important in your schedule, and it's my class. So there's really only one planet that's really important to all of us, and that's our planet. And so I'm going to focus mainly on geospace. There are some very interesting, not to diminish what's going on in the outer planets, Fran, but very interesting things that are going on out there. But you can only cover so much territory, so I'd like to drill down on what's going on in geospace. So the first part, before the break, and hopefully I'll get through it all, I have a few more slides at the beginning than part two. We'll focus more on things like structure and just persistent features, things that are there all the time, and I'd like to give you some insights into why they're there and some of the physics that underlies them. And then in part two, we'll move over to activity in geospace and dynamics and how these things vary. And I hope I don't preempt some of the things that John Foster will talk about tomorrow. I noticed that he's talking about things that have to do with variations over the solar cycle, and I will say something about that as well. Okay, so part one, and please interrupt as we go along. I'm sure that somebody who came earlier this week talked about typical properties in the solar wind. There are different ways to slice and dice the properties. Some people do it by the slow and fast solar wind, and I'm not going to go through all of these things. I hope that you've already seen them, but I include them here for reference because these slides are available, and they give you some numbers to work with, and we will use some of these numbers a little bit later on in the particularly when I talk about drag on the solar wind due to the magnetosphere. One of the most important parameters for the interaction with planets, in particular geospace, is the Mach number of the solar wind. It's super fast. As you know, in MHD there are three modes. There's the slow mode, which is kind of like a sound wave, compresses the fluid. There's an intermediate mode. Essentially, it's the transverse electromagnetic wave, the Alfvén wave. And then there's the fast mode, which is a hybrid of acoustic and basically it's a magnetosonic mode, and it can compress the magnetic field and the fluid. And the solar wind is super fast. And so we would expect shock waves to occur due to the speed of the solar wind. Now, the intermediate mode, yes, please.
That slow and faster slow wind just to random moments, to typical values. For example, the helium abundance is high, it was faster slow inside the general pattern, or just for this.
These are averages, and so I think, you know, there's a distribution of properties of all of these parameters over, you know, for any given set of conditions. And these are just means for the solar wind that originates from these regions, streamer belt and coronal holes, which give rise to the slow solar wind and the fast solar wind. Okay. Okay. So the two modes that can form shocks: slow mode, fast mode. Intermediate mode won't form a shock unless the fluid is anisotropic. And as you know, when an aircraft moves through our atmosphere supersonic speeds, it sets up a shock wave. It's a fascinating experience to be standing somewhere and have one of these things pass over you. And there, the shock wave stands out in front of the object and moves with the object. The solar wind, on the other hand, encounters this essentially fixed object, the Earth. And so a stationary shock wave is set up upstream of the Earth's magnetosphere. And to give you some insights into the nature of these shocks, so what you see on the left is some features illustrated of a slow mode shock, a discontinuity associated with the slow mode. And such a mode might be set up if the fluid passes by an obstacle at a speed greater than the slow mode speed in MHD, but less than the fast mode speed in MHD. And then a fast mode wave would be set up if the speed is super fast, which the solar wind is. And there are a couple of interesting features associated with these shocks. So for the slow mode shock, as you can see on the left, the magnetic field downstream of the shock is bent toward the shock normal. That means that the tangential magnetic field on the other side of the shock is less than the magnetic field upstream, the tangential magnetic field. Just the opposite for the fast mode. And so if you ask yourself what kind of electrical current must be flowing in this shock to produce that discontinuity in the tangential electric field, as I've drawn it here, you see that the electric current density must be into the plane for the slow mode and out of the plane for the fast mode. As a consequence, in MHD, to first approximation, the fluid velocity is the E cross B drift velocity. And so if you take V in the upstream region and cross it in the downstream region and cross it into the magnetic field and then take the negative of that will be the local electric field. And so in the shock, the electric field for the fast mode points in the opposite direction to the electric current. That shock is acting like a dynamo, electric dynamo. It's converting gas dynamic flow energy into electromagnetic energy through the shock. Also, some goes into thermal energy. For the slow mode, it's actually a load on the solar wind in the sense that, or on the field in the sense that electromagnetic power is being converted into thermal energy in the shock. Also, kinetic energy is also being converted in the shock. And so J dot E is positive in that case. And at Earth, the fast mode shock is set up upstream of the magnetosphere. And it is the dynamo. It's the electrical dynamo. It's the mother of all dynamos for geospace. Most of the currents ultimately close on the bow shock and take energy from that dynamo that sits there. I'm not actually aware of anybody who's tried to simulate a magnetosphere with a very slow solar wind so that the shock is not fast, but it's slow. But it should have very different characteristics because the shock is no longer electrical dynamo for a slow mode. It's an experiment that I think we may do in the future. It occurred to me as I was preparing this. Now, those are very simple plane fronts. Usually when you do shock analysis, Rankine-Hugoniot relations, you do a plane analysis, and that's a reasonable thing to do locally. But the bow shock is far more complicated. There's a 2-satellite mission that was launched in the late 70s, IC-1 and 2, whose mission was to try to resolve the differences in space and time as those 2 satellites cross Earth's magnetopause. And I'll say more about Earth's magnetopause and also the shock. And this figure was an attempt to capture some of the phenomena that was revealed in that mission. So we have, for the magnetic field configuration that you see here, kind of pointing from upper right in this figure to lower left, those lines of frozen-in magnetic field in the interplanetary medium. Near the nose of the interaction with the magnetosphere, the shock wave is said to be quasi-perpendicular, which is to say that the magnetic field is normal, more or less normal, or close to normal, to the shock normal, the direction of flow. On the dawn side flank, the shock wave is quasi-parallel, and it is very messy, in part because the quasi-parallel shock is very much a kinetic phenomena. Let me just ask you, has anybody asked you or mentioned anything about the mean free path of a typical charged particle in the solar wind in the vicinity of geospace? Does that come up? It's like 1 AU, right. So these particles would appear to be ballistic. And yet, the characteristics of the shock that's particularly for QuasiPerp shocks that are established upstream of the Earth obey the Rankine-Hugoniot relations for MHD very well. How can that be so if the particles are ballistic? Because MHD technically requires collisions, Maxwell-Boltzmann distributions. And the answer to that is that there are a couple of different things involved. One, the magnetic field of the medium turns the charged particle orbits in the direction perpendicular. And so it serves like a collision, not exactly. And then the turbulence in the medium also scatters particles. So the particles see each other through the long-range Coulomb force. But at least for the dynamics perpendicular to the magnetic field particles, MHD is not a bad description, actually. I mean, there are places where it doesn't work, particularly when the scale sizes get smaller than the ion gyro radius. But it does an amazingly good job. And when people first started developing global simulations of the magnetosphere, it wasn't clear that they were going to be able to capture some of the things that were observed, and it works far better than anybody had originally envisioned. Now, I said that the shock was the mother of all dynamos. I show here a picture developed from a simulation. I will talk more about simulations after the break. So this is from a global simulation of geospace, and let's not worry too much about what goes into the simulation at this point, but just look at what's painted here in color. And so the color is the scalar product of the electric current density with the electric field locally in the equatorial or ecliptic plane of this simulation. And blue means fluid energy is being converted to electromagnetic energy. and red means just the opposite, EM going into fluid. And so you see the shock for this fast mode interaction with the Earth's magnetosphere is a dynamo. The magnetosheath, the region between the magnetopause and the shock, the magnetopause is a load. That is, electromagnetic power is being converted back into fluid energy there. And then in the tail, you also see conversion going on, but it's much messier and much more distributed. The tail is much more dynamic. If the solar wind is dead steady, the day side interactions essentially in MHD is essentially quasi-static. But the night side continues to just churn and percolate. It's a very dynamic region. And so not surprisingly, the conversion of electromagnetic power to fluid energy and primarily to fast flows in the magnetotail is spread out. The black line there shows you the X line in this case where there's a magnetic null in the equatorial plane. This is for a condition with due south IMF. And you see flow velocity vectors on this plot as well. Okay, so I mentioned the term magnetopause. So what is the magnetopause? What determines its shape and size? And I'll tell you at the outset that the upstream boundary of the magnetopause, essentially the stagnation point for the impinging solar wind flow, is that stands at about 10 RE upstream of Earth for typical solar wind parameters, if there is such a thing. It's really just average. And so you can get a pretty good idea of how the magnetopause is established by appealing to Bernoulli's law in MHD, which just says that all the various pressures along a cross-sectional area of a stream tube should be constant. And so let's look at those various pressures down here in this table. So I've made this column here are the values in the upstream solar wind, and these are the values inside the magnetosphere. And I'm not really saying anything about the values in the shocked solar wind between the shock and the magnetopause. What we see in the solar wind is that all of the energy, the pressure, is in the dynamic kinetic energy of the solar wind by 2 orders of magnitude. In the magnetosphere, on the other hand, the flow energy, unless you get way out here in the magnetotail near the X line, but on the day side, the flow energy is quite small. The thermal energy, the magnetosphere tends to be quite a bit hotter than the solar wind, but much more tenuous. So typical particles densities in the magnetosphere are 1 per cc or less. In the solar wind, maybe more like 10 per cc, but much colder. But the magnetosphere is characterized by the geomagnetic field, and so the magnetic pressure is dominant in the Earth. So the first approximation, the magnetopause occurs, at least on the upstream side, where the magnetic pressure of Earth's magnetic field, stands off the dynamic pressure of the solar wind. The Lorentz force is intimately involved in establishing that effect, because when those charged particles that are weakly magnetized in the solar wind encounter the magnetic field of the Earth, they immediately start turning in their Larmor orbits. That's a microscopic view of what the fluid equations do in a macroscopic sense. Okay.
Bill?
Yeah. You mean this term here?
No, the numbers. Look at the column. Solar wind adds up to 1.
Oh, well, mind you, yeah. So this value is upstream of the shock, and that through the shock, the solar wind is slowed down. So maybe not a factor of 2, but these are values that I took off of, I think, the second chart I showed. So yeah, if you use average values, yeah, thank you. Yeah, thank you for pointing that out. Because when I put this table together, I asked myself, is that going to be a problem for people? And obviously it is. But the students get it, Fran. But I just have to accommodate you. Okay. All right. So near the stagnation point, basically the balance is between kinetic energy, kinetic pressure of the shocked solar wind and the magnetic pressure of Earth. But as the solar wind starts moving around here, and at some point it actually becomes supersonic again, and then it starts moving almost tangential. There's no longer a normal component to the dynamic pressure anymore. And so at that point, the thermal pressure in this shocked solar wind magnetosheath region starts to balance the magnetic pressure here. And people have worked on empirical formulas to try and predict where that boundary is for certain conditions. Oh, thank you, yes. So I'm not sure I understand the question. Keep going. Well, what happens is, I mean, okay, the question is, at the subsolar point, the energy has gone into thermal energy right at the boundary. And it is true. And in particular, for northward IMF, there's a pileup of magnetic flux, and the dynamic pressure is not doing it. But nevertheless, the kinetic, if you want to get a sense of where that boundary is, you can't use the thermal energy. You have to use, what you really need to do is use a full fluid model with a magnetic field, or a model for the Earth's magnetic field, and solve the combined equations when that kinetic energy is going into thermal energy, and so on. So you're right in that sense, but nevertheless, I think that if you tried to determine the location of the boundary from upstream solar wind parameters based on thermal energy, it wouldn't work. It's much too low to stand off the magnetic field of the Earth, so that there's a RAM associated with the kinetic energy of the Earth.
Also, they mentioned the vector. I'm wondering that's because that's actually the dipole magnetics. When you when you have due to the current rate at the magnetopause, you will double the magnetic pressure. That's probably why the vector two.
Yes, you get more magnetic pressure just inside the magnetopause. Yes, you're absolutely right. And let me go to the next slide. And what you see here is a real calculation now, not a sketch of kind of physical concepts. But back in the 60s, people were worrying about, okay, so where is the magnetopause? Can we predict it? And so Spreiter et al. Used a model for the solar wind, and they specified a magnetic field model for the Earth. This was not necessarily a dipole. You can use a more realistic model. And then calculated the location of the magnetopause for that given magnetic field model, and the streamlines and so on. And so you get a pattern something like this. So if you go in and look at the details of what the fluid is doing right upstream of the magnetopause, you will find it can't be dynamic pressure because it's gone to zero at the stagnation point, and it's going into thermal energy. Okay, so we have a shock, we have a magnetopause, and inside the magnetopause, that's what we normally think of as the magnetosphere and geospace proper. However, electrical currents flow right through the magnetopause out to that shock. So the shock is not really a separate thing. It's not a solar wind thing. It's part, and in fact, things that go on inside the magnetosphere can change where that shock occurs and its shape, and the magnetopause as well. So they're coupled, but when we speak of the magnetosphere, we're generally talking about the region inside the magnetopause. Now, another early concept that was developed by Jim Dungy was the concept of magnetic reconnection and what's now come to be called the Dungy cycle. And I'm not going to say too much about northward IMF. Let me talk about southward IMF first and just go briefly to it. So if you have due south interplanetary magnetic field, and of course by convention the Earth's dipole comes magnetic field emerges from the South Pole and goes up into the North Pole. And so there's a point where the magnetic field of Earth can be equal and opposite to the magnetic field of the interplanetary medium carried by the solar wind. And of course, the solar wind will continue to press that magnetic field that's embedded in it up against the dayside magnetopause, and eventually that magnetic field can become equal and opposite, essentially, to the Earth's magnetic field on the other side. And in that case, then, and that's a very narrow boundary layer, typically. A current layer develops there. In fact, you know there must be an electric current sheet there because the magnetic field reverses across this point here. And that layer is thin. In fact, it violates MHD there. So the MHD physics that describes the macro system doesn't do a very good job in describing the details of what goes on there. However, MHD still does a remarkably good job in describing the overall rate of reconnection, primarily because it's driven. The solar wind's ramming that magnetic field into the dayside magnetopause. And so some studies that have been done with MHD simulation show that it gets the rates right for not necessarily the right reasons, but because the external, the forcing of reconnection from external conditions is being described adequately by MHD. And so this null line goes all the way around the Earth on both sides, goes around the equatorial magnetosphere for this configuration. And then there's magnetic field lines are brought back together here. They're pulled, and I'll show in another slide, they're pulled tailward. Reconnection also occurs in the magnetotail. And on the flanks, it's quite weak because on the flanks of the magnetopause, that flow is almost tangential. So the magnetosheath or shock solar wind is convecting the flux away from the boundary tangentially downstream rather than normally into the boundary to force reconnection. So the reconnection rate becomes quite weak on the flanks. For northward IMF, you can't have reconnection here because the field's...
Can I just ask you to clarify? You said that configuration extends all the way around.
Yeah.
You then followed to say that the reconnection will be inefficient because of the flow
Right.
being tangential. But do you really mean all the way around, or like how far around?
Well,
Can I attend to that question? When you say it's null, it's a component of northward and a component southward.
yeah.
There's a spiral direction, isn't northward.
Sure. These are idealized conditions, and there will always be some other component of the magnetic field. There will be a component toward or away from the sun in general, and there will be a component normal to the plane here. And so that, and I'll say something about that later on. But it does change where reconnection occurs, and it changes the kind of topology of the magnetosphere, the open-closed boundary. So here you see an example. So this is from a simulation. Here's the X line, all the way around the null line. And we've gone through and calculated the reconnection rate all around this line. And there's actually a 0 point on each flank side. And so flux is being brought in here on the day side or sunward of that point, and on the night side, flux is being reconnected and being shot earthward on the next side. So the nature of the reconnection process is different on the day side and night side for that reason. But the main reason why the reconnection rate goes essentially to 0 or becomes quite weak on the sides is because the flow of tangential flux just doesn't enable reconnection. Okay, so to give a little bit more perspective on what happens. So basically, this is a figure which is from, I think, one of the textbooks that may be on that table back there. And the frozen-in magnetic flux is brought into the vicinity of the magnetopause, and so this field line 1 is just now reconnecting. It's got a southward component here. It reconnects, interconnects with a geomagnetic field, and so now what had been a closed field line inside and and an interplanetary field line outside now is interconnected. So it comes in, goes up, and goes down to Earth. So we call these open field lines. And then the flow in the solar wind, or shocked solar wind, the magnetosheath, carries that field line. So it's frozen in, it's ideal up here. And so that field line becomes 2, 3, 4, 5, and so on. So take these field lines and go deep out into the solar wind, far, far away from the Earth's magnetosphere. Those field lines, the ends of those field lines are moving with the solar wind. They don't care about the magnetosphere if you go far enough away. And so what you can see is going to happen is that there's going to be a bending of the field line as it's carried tailward by the solar wind, and it's going to be brought back in. And mind you, this field line is going way out here and then back up. And so there's a tangential stress that pulls that field line downward, which enables the reconnection process here. And so the Lorentz force in MHD has these two components, as you probably know. There's the magnetic pressure, which has a sense of an ordinary pressure, normal to a boundary. And then there's this magnetic tension associated with the stresses of along the boundary and inside the magnetosphere as it's carried earthward. Okay, so there's a nice animation that was developed here in this building by the education group, and I think Mike Wiltberger was involved in running some simulations. So the results that you see in the left panel here actually have a heritage to an actual physical simulation. It's not just a cartoon, but it's been cartoonized, if you will. Okay, so what you see here is that southward field's brought in, reconnects, opens the field line, drug tailward, reconnects. That field line comes back earthward. The only one that's shown here is the one that goes around the dawn side of the Earth. There's a counterpart that goes around the dust side of the Earth. So actually, there are many field lines. It's just to show one in particular. And then associated with that, with the feet of the field lines that are down in the ionosphere, there's a circulation of the field lines that looks like this. So here on the dawn side, over the polar cap, anti-sunward, and then return flow sunward at lower latitudes on the two sides. And this bending of the field line that you see here, that kink in the field line, is associated with the generation of field line currents, which flow down to the ionosphere and close in the ionosphere. And I'll talk more about that in just a minute. An interesting thing that you can ask yourself, okay, you got this obstacle sitting there. We know that when an aircraft flies through the atmosphere, there's a drag on it. Car manufacturers are doing their best to reduce that drag, even at slow speeds. And the question is, what kind of drag does the magnetosphere exert on the solar wind? And the drag coefficient is defined as the force, the component in the direction of the flow velocity. And the drag, that's FD is the force, and then the drag coefficient is a measure of the incident kinetic energy in the fluid multiplied by a reference area. And I didn't actually include in my table here anything for aircraft because the reference area for aircrafts are more complicated than simple objects. But in the one of the heliophysics textbooks, and in particular the first one, I don't think it's actually called Volume 1, but it's the first textbook, Chapter 11 by Toffoletto and Cisco. They actually calculate the drag force using several different simulations, global simulations, and they're within a factor of 2 of each other, which means that the numerics do matter, how you actually solve the equations. And so I use their numbers to try and get an estimate of the drag coefficient for the magnetosphere. And for the reference area, I took the cross-sectional area, circle, of the magnetosphere at about the plane of Earth. And that's approximately 15 RE radius. So the cross-sectional area is pi times 15 RE squared. That should be 15 squared RE squared there. And so the drag coefficient for the magnetosphere turns out to be 3. It's quite large, actually. And the reason is in large part due to that tangential stress, that that stress on the field lines that are anchored in, ideally, into the solar wind far away, those field lines and the flow that is connected to those field lines is seeing the effect of them being anchored down in the conducting ionosphere. So those stresses are exerted. And to give you some perspective, so if you take a sphere and you move a sphere through low Earth orbit, above the region where the size of the sphere is larger, less than the mean free path, so LEO, 800 kilometers orbit or something like that, you can do a calculation to find out what kind of drag such a sphere would encounter just due to ballistic specular reflection of particles off of it. And that drag coefficient is about 2. And so the magnetosphere is specularly reflecting, and also it's got this tangential stress, which a sphere in the upper ionosphere and thermosphere does not. And to give you a sense of others, flat plate oriented tangential to the flow, the drag coefficient's quite small. In ordinary fluid, the drag coefficient's like 0.1 to 0.5. Most cars, 0.2 to 0.5, and so on. So magnetosphere is exerting quite a bit of drag on the solar wind. Okay, we need to talk about induced currents in geospace. And they determine the structure of the magnetic field there and the shape of the magnetosphere. So the shape of the magnetosphere is dependent on these current systems. It can't just be a dipole because the interaction with the solar wind causes currents to flow, and that distorts the shape of the intensity of the magnetic field in certain regions. So for this situation, you see an interplanetary magnetic field that's oriented southward coming in with the solar wind. Close to the Earth, the magnetic field, if there weren't a South Atlantic anomaly, would be approximately dipolar. And then as you go away from Earth, you start picking up contributions from the current systems that are flowing in geospace. One of the important current systems is the so-called ring current. This is a current that flows around Earth. As you see here, it flows, if you look down on the North Pole, it would be going around like this, looking down. I think that's clockwise, in a clockwise sense. Out of the plane on the night side, into the plane on the day side. This current can be understood through MHD as a diamagnetic current, but the fact of the matter is the reason it really occurs is because of the gradient curvature drift. So the particles are, charged particles in geospace are moving in a magnetic field that has a gradient and a curvature. And ions in particular, due to their larger mass, move faster for the same energy than electrons. And so most of this ring current is carried by ions, which are drifting in the direction of the ring current here. Electrons, of course, go in the opposite direction because of the different charge. So if you ask, okay, suppose that we have a ring current, and this ring current depends on ambient conditions in the solar wind. Sometimes the ring current can be very large, sometimes it can be very weak. And so as the ring current intensifies or subsides, the induced magnetic field due to the ring current is going to change. And so on the night side, you see that there's the magnetic field. If you use your right hand, there's a magnetic field on the earthward side of the ring current, which points downward, opposes the dipole magnetic field of the Earth. Dipole magnetic field comes out of the south, goes up into the north. So this current system induces a magnetic field which opposes it. And same on the day side. So all around the Earth, the ring current is producing a magnetic field which opposes the geomagnetic field. And on the outside of the ring current, of course, the ring current is not a line, it's not a wire. It's very distributed in space. But on the outside of the ring current, it enhances the geomagnetic field, and that in part gives some inflation to the magnetosphere. It adds to the dipole magnetic field there. There are a couple of other important current systems. The neutral sheet, so just as drawn here, you can see that the magnetic field going into the North Pole and out of the South Pole here, if you go far enough out where this thing is dragged tailward, clearly there has to be a current sheet here to sustain that magnetic field. And similarly, on the day side, there has to be a current flowing in the magnetopause to enable the transition of the interplanetary magnetic field to the geomagnetic field, which is in opposite directions there. Okay. So, so we have these two. These are three of the most important current systems in geospace that determine the structure. There's one other one that's quite important for magnetosphere ionosphere coupling, and those are the field line currents. So, here's another view. Here's the magnetopause current. Here's the tail current again. There's a ring current flowing around Earth. And then when any of these currents divert, okay, in MHD, the electric current must be divergence-free. The displacement current is ignorable in MHD. That means that if you take the scalar product of Ampere's law, or the divergence of Ampere's law, you find that the electrical current must be divergence-free. So perpendicular currents can be converted into parallel currents at through various parts of this system and in various regions. The ring current is diverted into so-called region 2 currents. I'll say something about that later on. Processes in the outer magnetosphere sustain so-called region 1 current field line currents. And so these are currents that in one sense are force-free. That is, the current is parallel to the magnetic field and they connect what's going on between the magnetosphere and ionosphere. Thank you, yeah.
These ring currents can also be below electrojets to an altitude above the surface. Would you say they are?
The ring current flows mainly near the equatorial plane, but it does flow above and below. It extends from, and again, these variable depending on ambient conditions in the solar wind, but can extend from 3 RE out to 6 or 7 RE. So imagine it's this thing that's circulating out there. The electrojets are down in the ionosphere. So they're flowing in the E region, dominantly 120 kilometer altitude above the surface of the Earth at higher latitudes. I'll say something about electrojets too, if I have time. We're supposed to be stopping pretty soon, aren't we? I don't want to stop, but I want you to have a break. Let me go a little faster here. And actually, there's one thing I can truncate out of this. So these so-called region 1 currents that are flowing from the outer magnetosphere, there are at least a couple of different mechanisms. Well, 3 if you allow for an anomalous viscosity in ideal MHD, but forgetting this viscous drive term here, these two terms just come straight out of MHD. So if you take the MHD momentum equation and take the scalar product of it with the magnetic field, then you can back out the perpendicular component to the current. You can ask what can generate perpendicular currents in Earth's magnetosphere, some of these currents that we see. And so there's inertial drive and pressure drive. And so along the edge of the magnetopause, where the flow is moving anti-sunward, more or less, this term can be quite important in generating currents. So what will happen is there will be a perpendicular current, as shown here, flowing earthward in this projection. And then if there's any divergence in that perpendicular current, that's going to go into parallel current or other types of perpendicular current. And so that's one source of the region 1 currents, and it's more dominant on the day side. On the night side, because of night side reconnection, there tends to be a hot spot in a high pressure region, kind of in the middle of the magnetotail here, or near Earth plasma sheet. And so pressure drive can be quite important in generating currents on the night side. And then this boundary is quite messy. Yes?
Can you explain the LLDL acronym for me? I think I might have just missed it.
Oh, sorry. Yeah, right. Some of these slides I adapted from presentations I'd given that were focused on the low latitude boundary layer. So, okay. So these are some of the processes that give rise to those field line currents I talked about. Okay, now, how do they close in the ionosphere? This is the basic equation So given a field line current that flows down into the conducting ionosphere, the ionosphere, if you go low enough down, is collisional. So now we're back to bona fide collisional processes as opposed to collisionless in geospace. And so, and because the ionosphere is also embedded in a magnetic field, the conductivity is anisotropic. There's a Pedersen and a Hall current. Pedersen current, what happens is that as the electric field comes down, is impressed down into the ionosphere, as you go down, first the ions demagnetize because their Larmor radii are larger than the electrons. So when the ion gyro frequency becomes greater than the collision frequency, then the ions stop being magnetized, the Lorentz force is not dominant, and they start moving in the direction of the electric field. So the ions carry a current in the direction of the electric field. That's called a Pedersen current. The collisions there are between ions and neutrals primarily, because the neutrals are the dominant species in the ionosphere. The electrons, on the other hand, are still magnetized. They're still E cross B drifting, and so they carry a current perpendicular to the direction of the electric field. So the Hall current's carried by the electrons there, and the Pedersen current's carried by the ions. And if you enforce current continuity, and this is what Ohm's law looks like in the ionosphere, Bn is, if you're in the inertial frame of the neutral gas, the average velocity of the neutral gas, then this term goes away, and it's not present up here. And if you assume that the electric field is electrostatic, which for relatively slow time scales and large spatial scales is valid, then you can replace E by minus gradient of an electric potential there. And so you put this in here, put this equation in here, assume the electrostatic condition, integrate over the height of the conducting layer in the ionosphere. So capital sigma here means height integrated conductivities. And then this equation determines what's going on in the ionosphere. So what people would normally do is to say, okay, the field line currents are flowing in from the magnetosphere down to the ionosphere. This is like a source in this Poisson equation. If we know the conductivity in a height integrated conductivity, then we can solve for the potential everywhere in the ionosphere. And you can show, you can prove, it's essentially a theorem, that lines of equal potential are streamlines in the ionosphere. So these lines that you see here are equipotential lines, and by virtue of this right here, so B hat is the unit vector in the direction of the magnetic field, E is the electric field, so this term is in the opposite direction to the flow, E cross B flow. And so Hall currents flow sunward over the polar cap, but the flow is flowing anti-sunward. E cross B drift is anti-sunward over the polar cap. Okay, so, yeah.
So for field line currents and Pedersen Hall currents, is there a distinction, like at some altitude we care pretty much only about field line, and then below that altitude Pedersen Hall take over and field line stop being like influenced by the field current system?
Right. So, so the Hall currents flow primarily in the E region of the ionosphere, up to 150, maybe 180 kilometers, depending on exactly how exercised things are down there. The Pedersen currents are also dominantly in that E region. However, they extend up to higher altitudes, and even depending if there's a fair amount of soft electron precipitation, which deposits its energy above the E region, you can get a significant enhancement to the conductivity up on the bottom side of the F layer of the ionosphere, if those terms in E region and F region mean anything to you. But so the ions and electrons are E cross B drifting to a good approximation at the F region peak and above. And below that, the ions start demagnetizing, and they're seriously demagnetized by the time they get down to the E layer. Electrons still magnetize. Electrons don't demagnetize until they get down in the atmosphere. Yeah.
So can we say with relative confidence that above the F region, the only current system we're actually really looking at until we hit like magnetosphere levels is the field line current? In a quasi-static sense. Now, in that region, at time scales of 10 seconds or less, Alfvén waves
can carry significant polarization currents there. I haven't said anything about that, and that's basically a time-dependent effect to a large degree. And so, yes, above that, dominantly field of line at large scales and long time scales. And then as you get to smaller scales, alphanic currents start to become important. And then when you get out into the outer magnetosphere or the equatorial magnetosphere, then things like ring currents and so on, and diversion between ring and field line current start to become important. Okay, so I just want to make some contact with some real stuff here. So this is a plot. You can get this from CC if you Google CCMC Wymer model. It'll take you to a page, and you can put in whatever solar wind parameters you want, whatever day and time of the year you want, and it'll generate a plot like this. And you can have it do, for example, what I've done here is ask it to give me the current density and color, and the streamlines or the equipotentials contours. And so that's what you see in the black lines there. And so this is a model that was developed from about 2,500 low Earth orbit satellite passes from the DE-1 satellites, and that satellite that was launched in, I want to say, the 80s. And so Wymer took all this data, electric and magnetic fields, binned it by various solar wind conditions to create an empirical model. And it's widely used, one of the most widely used models to at least get a sense of what's going on. Of course, as one of our colleagues, Rod Helis, will tell us, if you look at any given time interval, the system never looks like this, because this, just take a whole bunch of averages and it just smooths out all the variability. So you always have to be cautious of that. But I'm gonna pause here. So I'm gonna ask you a question. Okay. So if these are equipotentials, and if on the dawn side here, where you have that plus sign, the potential is positive, and for this case it's 46 kilovolts. That's a potential maximum. And on the dusk side here, there's a potential minimum, minus 52 kilovolts. Over the polar cap in the middle of this plot, what direction does the electric field point? That's the first, this is a multi-part question. That's a simple question. But it points from dawn to dusk, right? Minus gradient of the potential. Okay, so what direction is the flow velocity? Well, if this is northern hemisphere, magnetic field's in, so over the polar cap, toward the night side. That's what you'd hope was happening, because field lines are being pulled over the top region, right? Do that again?
I didn't follow it.
You didn't follow it?
I just taught intro physics.
Okay, let me review that. So the electric field is minus the gradient of the potential. So the gradient of the potential is going from the minimum to the maximum, so take the opposite sign. So the electric field has to point that way. The magnetic field is into the plane if we're in the northern hemisphere, and so E cross B is over the polar cap anti-sunward here. Okay, so that's how it works. Okay, so now we got the electric field here, and so where would you expect? So remind you, there's a conductance here, and I'll just tell you the Joule dissipation in the ionosphere. Basically, well, you can say it's I squared R, okay, or voltage over R squared. So there's a conductivity. So where do you expect the largest Joule dissipation in this region? Just suppose the conductivity is uniform everywhere. Where would you expect the Joule dissipation to be largest? This is a little bit harder than the other parts. What's that? Well, so where might, if the conductivity were uniform everywhere, okay, and the Joule dissipations goes like sigma p E squared. So the conductivity, sigma p, the Pedersen conductivity, times the electric field squared. Where's the electric field largest in this figure? where the streamlines are closest together, or where the equipotentials are closest together, the gradient in the potential is largest. And so therefore, in this plot here, we'd expect large electric fields here, large electric fields over here. And so another way to think about that, which kind of makes sense, is that the color here is field line current, and so blue is out, red is in. So ask yourselves, if the divergence of J is 0, and we have currents flowing in and out into this region, then at the level of the ionosphere, they have to go from field line to perpendicular to close. Otherwise, we start building up charge. So if it's in here and out here, one closure path is right across the polar cap. So that's the electric field that we were just talking about, right? So there's the Joule dissipation occurring in the polar cap. But another closure path is from this current in to a low latitude path. And these are the so-called region 2 currents at lower latitudes. That's just purely a morphological description when people didn't know what these currents were due to. And so there's another closure path here. And so you see the potentials are closer together over here as well. And basically what happens is that when satellites fly over this region at higher altitude above the conducting layer, they see Poynting fluxes flowing from the magnetosphere down to the ionosphere. And those Poynting fluxes are largest where the Joule dissipation is largest because something has to feed that energy. And so electromagnetic power is flowing in from Earth. Here's another, this is an example of Rod Helis's admonishment that things don't look like that in reality for any given event. So there's a satellite constellation, Iridium, primarily used for global cell phone coverage, and Brian Anderson at APL has gotten them to give him the engineering magnetometer data. Their noise is his signal. And from that, you can take the magnetic vectors from 66 satellites and do an inversion to calculate the expected field line currents. And so this is with 10-minute resolution to acquire enough data. And so this is at center time here. And so you can see there are quite a few minima, maximum, although still you can see this inward current here, outward here, inward here, outward here, region 1, so-called region 1, region 2 currents.
Is this a good place for overlooking?
Yeah, I think it is. Thank you. So let's take a break. 15-minute break.